I posted the slides on the chat. Okay, let me start the okay. Okay. So we're chugging along in this chapter 9 on using modular arithmetics, and one application is well, an application, a kind of a related issue is the representation of integers in different bases. So the ones you're most familiar with are binary and decimal. Okay, but you will see the relation to a modular arithmetics in a sec. This is all of it is in 9.6. Maybe at the end we'll go to 9.7. I'm not sure. And now I'm not sure if we'll get there. Okay, so we use base 10 representation, right? In I believe everybody in the world uses it, right? Like it used to be that some other cultures had other decimal systems. I mean, other systems, but I'm not sure if anybody really uses those. You come from all over the world, so share with us on Piazza if you know of other decimals, other systems still in existence, or if in recent history of your country or some country in the neighborhood, other counting systems were used. So so in the decimal 3045, we learned that what these digits represent are basically multiples of 10, multiples of 100, multiples of 1,000, etc. Right? So these are different powers of 10, and in the same sense, the least guy is the multiple of a power, the 0th power of 10, which is a 1. So in general, you can have more digits here, right? This will correspond to higher powers of 10. And in computer engineering, you have very often base 2 representation. So, in a circuit, you can have either voltage or no voltage, 0 or 1. And so digital circuitry is all operating on bits. So which have only 2 states, right? 0 and 1. But in a binary, I can represent integers using the same method. Just take powers of 2. Okay, so now in order to express the same integer, I would use more digits in binary, because this is between the 3rd and the 4th power of 10, but this is between 9th and 10th power of 2. Okay, so I will use 10 binary digits, and here I only use 4 decimal digits. So I can do this with any base, right? So and note that in decimal, the only digits possible are between 0 and 9. So it makes no sense to have a digit representing 10. If I wanted to place a 10 in this position, I would just put a 1 in this position, right? So it would be a carry. The same with bits. It makes no sense to have a digit 2, because that's represented by a digit 1 in front of the higher power of 2. So here is the digits base B are in this set. So we introduced this in modular arithmetics. ZB was integers modulo B. So all remainders from integer division by b, which is 0 ... b minus 1, right? This is the highest remainder from division by b. So these are the residuals mod b. So and these are also digits in base b representation. So say base 7, you would have this set of digits. By the way, this is 7 digits, right? It's just you starting at 0, so you end at base minus 1. So in a base 7, 612 would be interpreted differently than 612 base 10, right? Namely this way. And so you can compute what it would be base 10. What integer does this represent? Of course, this integer is already written here, but it's written in a base 7 notation. So perhaps that's not like the most convenient for everybody. Let's compute it in a base 10 notation. That's this. Okay, so if I don't say what base it is, this is base 10, right? Because that's what we all do. Like we don't say base 10, right? We just assume that. Okay, so every integer can be expressed uniquely in any base. So a base every base is good. It represents, you can represent every integer in every base, and these are unique representations. So what's the representation of n? It's a sequence going from right to left, A0, A1, to as high as needed, such that this equation is true. And moreover, each of the HAs here is in this set, right? So each of these digits is in the proper set of digits for that base. So these things always exist, and moreover, we can compute them. So like to prove that they exist, like why don't we just prove that an algorithm that computes them is correct? It's by also we would imply that these things exist. And the leading thing is unique because we say that the leading digit has to be non-zero. If we didn't have this constraint, then it wouldn't be unique because we could continue with zeros and we would get the same number, right? So this constraint implies that it's a unique representation. Okay, so let's do some examples. So 452 base 6. Okay, we take this digit and multiply powers of 6. Where is the power of 6? Well, it's a 6 to the 0, and that's a 1. So that's why I don't even put here. And this is 6 to the 1, which I put as simply 6. Okay, but higher powers I'm going to put abstractly. Then I will evaluate them. Then I will cross multiply all of this and add. Let's look at binary. So it's best to start with the right-hand side because you know that you have to start with the 0th power and then increase the powers of the base, right? So let's write out all these powers in the standard notation, right? And then, because it's this way, you can keep yourself honest. Like, I mean, basically prevent yourself from making a dumb mistake. So now you see, okay, this is a 1. This is a 1 to the 0. So 1 times 1, 1. 2 to the 1 is a 2, but I don't care because it's a 0 in front. This is a 4. This is an 8. This is whatever, I don't care. And this is 32. So in fact, a binary, it's kind of easy because all it does, the bits basically select which powers of 2 should you take and which powers you should ignore. But nevertheless, it's better to write them down because this way, if you have a bunch of zeros here, then you might skip some powers of 2 and end up computing the incorrect power, let's say here, right? So write them down, and this way you will not make a mistake. So base 9, we do the same, right? Like you have consecutive powers of 9 starting from the left. This is a 1, this is a 9, and this is 81. And boom, I have some. Whoops, how did I get that? Okay, that's obviously a typo. I didn't notice this. Okay, this is some outrageous thing I just wrote here. Okay, did I make a mistake here? No. So yes, okay, no idea. I overlooked this. Okay, it's called the hidden math, right? Yes. Okay, so sorry, I will correct these mistakes. I don't really know how I had them. I overlooked them on the slide. All right. Okay, so please don't use these two lines to learn how to do it. Bases can be higher than 10. So base that is actually used in computer engineering quite a bit is the base 16. And since, so what are the digits base 16? Okay, well, it's a Z16, so it's all the way from 0 to 15. The problem with using higher integers is that writing this as 6, so let's say D is 10, 11, 12, 13. So D is 13. So if I, instead of writing D, I would write 13, then I would write 6, 13. And it's ambiguous because it's not clear whether the 13 refers to this character or it refers to a sequence of characters, 1 for 1 power of 16 and 3 for a smaller power. And these are not the same thing. Okay, so that's why we don't use integers higher than 9. We use alphanumeric characters, right? And honestly, you will not deal with higher bases than hex. So you just need to learn that in hex, this is the convention to denote the 6 missing digits that you don't have in Roman, or no, sorry, Arabic numerals. Okay, so how do I interpret 6D base 16? Okay, D, so again, I write how many powers? Just 2 powers of 16. 16 to the 0, 16 to the 1, because this is 0 power, the 1 power digit. And this 0 power is because D is a 13 and 6 is a 6. Okay, so I cross multiply whatever it is. Okay. So, okay, let's look at a 3-digit hex number. So I have 3 consecutive powers of 16, and F stands for 15, right? The last digit, last residue mod 16. So that's a 15. I put it here. E is the one before last, so that's a 14. I put it here, and I compute whatever this is. Okay. So whenever I have a number written in some base, okay, I can convert it to standard notation, decimal notation, using the same method, right? Whether this base is 16 or it's base 2 or base 7, it's the same method. How about the other way? So you have a number in decimal, and you want to convert it to a given base. Let's say hex, or let's say base 2, or yet another base. Why is E not 15? Because if I wrote 15 here, then it would be ambiguous. You would think, okay, is it a 4-digit hex number with the leading digit 1 followed by digit 5? Or is it a 3-digit hex number where the 15 at the beginning corresponds to this power of, of 14, sorry. Yeah, so that's why. Oh, okay. So people have some conversation on chat. Maybe I'm not responding to the questions really. Okay, how do you go back? So how do you encode from that? So we saw from an arbitrary base, I can go to decimal. How do I go from decimal to an arbitrary base? So here's a very quick recursive algorithm. It turns out that a representation, the digits that make up a representation of some integer n base b are as follows. The last digit can be computed straight away given n and b. It is simply a modular reduction of n base b. Okay, so like for example here, if I have 45, I know that the last digit is a 1 in a binary relation if I wanted to go back, because if I had a 0, then this would be a positive number because these are powers of 2. This is the only odd multiple. This is 2, 4, 8. So these can only give me an even number. This one can switch the number from even to odd. And since I have an odd, so I know that this last bit must be 1. And it is because 45 mod 2 is a 1. Okay, this in general works. Like 176 mod 6 is a 2, because 174 is a multiple of 6. Okay, and this will work. Of course, this one I messed up, so no. Okay, okay, what about the other digits? Okay, so you established the least significant digit. What about the rest? Well, this can be recursively computed by taking your integer and doing integer division by b. This is the remainder, this is the quotient. You now run recursively the same algorithm on the quotient. So this corresponds to, look, if I wanted to learn the base, what 45 is in binary, I first take a mod 2, this determines this bit, and then I take a div 2. I divide the rest by 2. What do I get? 44, 22. 20, this, if I forget about this digit, the rest is actually denote 22. You can check that this is true. And it must be true because 22, basically these higher powers, it just means that the whole thing shifted to the left. Okay, you can maybe see it, maybe not, but you will see it in a second, like just a proof that this works always. Okay, so let's say I want to compute, okay, so it's a recursive algorithm, but what's the base? I didn't say the base, right? But the base is kind of obvious, like if there's nothing further to divide, right? Like if n is already smaller than b, then that's your base case. At that point, you just output n, and that's it, right? So the base case is obvious here. What is the representation? Let's say we want to compute 35 base 5. So the least significant digit is going to be 0 because 735 is divisible by 5. So it's all expressible as some non-zero powers of 5 added up. And the 0 power, the 5 to the 0, is moot, right? So I zero it out with the last digit being 0. Okay, now I take a div of this, and this happens to be 147. So now I take a mod 2, and I recursively run to compute the next digit, going from the right to the left, right? Going from the least significant digit to the left. So 147 mod 5 is a 2. So the next digit is a 2. And now I take 175 mod div 5, that's 29. And I recurse. 29 mod 5 is a 4. So I have a next digit. Then I do a div, it's a 5. So 5 mod 5 is a 0. So I didn't hit the base case because I'm not yet, I cannot output 5. 5 is not a digit base 5. I have to have an integer which is smaller than 5. Okay? So, but I'm gonna get it in the next move because 5 mod 5 is a 0, so this is a digit. 5 div 5 is of course a 1, and that's my next digit, and that's the end because I have an integer that is in Z5. Okay, and now you can check that this number is indeed 735. When you do it, you should always verify, because going back is easy, right? Multiply this by the appropriate powers of 5, and that's what you should get. Okay, so always test this, because there's a bunch of mods, divs, maybe you made a mistake at some point. Verify it. Okay, and I have the verification here that I didn't remember I have it. Okay, so I only took look at the positive powers of 5. So this is 2 to the 2 times 5, 4 times 25, and a single 625. So this is this, and indeed I get 735, right? Okay. Why does this algorithm work in general? Okay, so here it is, right? If the same algorithm, but like explicitly written. So if the number is smaller than the base I'm already done, that number is my digit. And otherwise, I recursively run it on n div b, and that gives me all the digits except the last one. The last one I compute this way, and I concatenate them, right? So you can express this even faster, right? Exactly like this. All right, why does this algorithm work? So here it is in a shortened notation. How would we prove such a thing? Well, big surprise, by induction. Because it's a recursive process, it defines output on some higher elements as a function of the outputs on the smaller elements. So in order to argue anything, we'll be arguing using recursion. What is the base case is that your integer is smaller than the base, in which case the base case kicks in. And indeed, that's a correct thing, because if an integer is smaller than b, then n in base b is the same as n in decimals. Okay, now the recursive or the inductive step in the proof. So say your algorithm was running on an n, and it wasn't smaller than b, so it hits the base this recursive step. Let's call n div b n prime. That's going to be the argument into a recursive call. And I'm going to call the n mod b part a0. Okay, because that is indeed, this algorithm will output this value n mod b will be output as the last digit in the output of this algorithm, right? This will be the last digit, the least significant digit. So I'm going to call it a0. Now, remember the basic thing about div and mod. They maintain this relation. Okay, the n mod b plus n div b multiplied by b gives you n. So this is the basic equation that we repeated every lecture for like the last week or so about integer arithmetics. So this equation holds. Okay, and now let's say that this call outputs the following digits. Okay, like a1 to ak for some k. And now by inductive assumption, you can assume that on a smaller integer, this was correct. Okay, so that's how we argue about the recursive call. Let's assume that the smaller value, when it was called, returned the correct output. And based on that assumption, we'll argue that this call on the higher value, utilized these outputs so that they are correct as well, right? So from correctness on some smaller values, we're going to get correctness on larger ones. So, so if the base B representation of n prime and div B were the following digits, then what this guy returned was just concatenating them, right? He just took all these and then stuck an A0 at the end, and that was the representation it returned. So the argument that we must make is the following. If this is, we can assume the recursive call, this is a correct representation base B of n prime. If under this assumption, we'll argue that this is a correct base B representation of n. Okay, that's all we have to do in this recursive step of the inductive argument. So that's what we assume that this is correct by inductive hypothesis. And what that means is that n prime can be expressed in this way, right? Because that's what it means, that this string is a base B representation of n prime. And be careful about the shift. I'm calling these digits starting from 1, but they are base B representation of n prime, which means that I have to start with a 0 power. How many of them I have? K. So I end up with the k minus 1 power on the left-hand side, right? There has to be k of them, and I'm starting from 0. Okay, so that's n prime. And but if n prime is this, and n is related to n prime as so, because that's the relation that happens when I'm n prime is n div b and a0 as n mod b, this relation is guaranteed. Therefore, it follows that n, which is b times all of this stuff, plus a0, I can now rewrite as b times this stuff plus a0. And what this will do is it will just hike up the powers of b in all these products, right? So it will get me this, and I'm done, right? Because indeed, this shows that the string from ak to a0 is the correct mod b representation of n. So reducing to a base, reducing an integer to some base, representing an integer in some base, is exactly like just rewire yourself as if all the computations are mod based, and then think of the number as mod that base, and then divide the rest by the same base, which ends up shifting your digits to the right, and then recurse. And that's what we do in decimals. If you think of the decimal string, like, what is 1279? You first look at the 9. Well, that gives you a bucket between 0 and 9, mod 10. And then what do you do with the rest? Well, this gives you this sort of scaled up buckets of how many hundreds you have, how many tens you have here. Instead of scaling buckets, you can shift your digits and now just divide the number by 10, and then place the next digit in the appropriate bucket. Okay, maybe I don't know if this was helpful, but it's really the same procedure that we do to understand what even decimal representation means. Okay, some shortcuts here. If so now you can go from any representation to decimal. That was the first few slides. Now with this recursive algorithm, you can go from decimal to any base. So you basically can go from any base to any base, right? Like because you can go to decimal and then from decimal to the target base. But sometimes you don't need to. If you have a base and you want to represent it in a different base, but that new base is actually a power of the base you start from, then the whole thing becomes much faster. The flagship example is a relation between representing numbers in binary and representing number in hex, base 16. The two bases are related by this relation, right? 16 is the 2 to the 4th. That means that every chunk of 4 digits base 2, so here in this case 4 digits base 2, corresponds to a single digit base 16. Okay, and you know, if you have some other bases, this will work as well, but that's the most immediately useful case for us. And that explains why hex is used in computer engineering, because if everything is base 2, in the wires are base 2, but normally, you know, we don't have like arbitrary number of these. We don't have 9, we don't have 11. We split these bits into bigger chunks, like a byte that has 8 bits, right? Or a word or whatever that has 16 bits, or a long or an integer, whatever, some other types, right? They basically go by number of bytes, which is number of 8-bit segments. So because writing stuff in binary, you know, perhaps is good for circuits, but it's not really good for us to remember anything. If one programmer wants to communicate with another, it might be easier to represent it in some ways that like is a little more succinct, and also easier for us to process. Base 16 is perfectly exactly that. It is more succinct because if you start from, say, 2 bytes, so 4 chunks of 4 bits, then you end up with only four hex characters, because every 4 bits just collapse to a single hex character. So that's much easier to read off. You know, like let's say I want to read off a cryptographic key or a hash or some other element in the crypto system. If I had to read the bits, that would, I'm sure I would make a mistake and I would lose, you know, where are you? If I convert it to hex, I have now 4 times less elements, and they're more distinct to me, right? To my mind. So easier to write, easier to communicate, and easier to avoid mistakes in human-to-human transmission. So here is the 16 hex digits and the corresponding binary digits. And you can see, okay, if that I went all the way from an all 0-bit string to an all 1-bit string. And indeed, what's the highest, what does this represent in decimals? It's a 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So it's a 1, 2, 4, 8. 1 plus 2 plus 4 plus 8 is 15. Okay, so there is a 1-to-1 correspondence between hex digits and chunks of 4 binary digits. And you can now use it to convert binary into hex very quickly. Just divide them visually into groups of 4, like so. And this will also allow you to make to avoid a mistake at the end where it is not exactly a group of multiples of 4, right? There is a digit missing, right? So this is basically 15 bits. Okay, but that's okay. You go right to left. So if you go right to left, what this stands for is really this group of 4 bits, right? The leading bit here is 0. If we want to force it into a group of 4, then that would be the group of 4. And now you just look up these tables and you translate it into hex each, right? So it's a much faster algorithm. I don't have to evaluate this as a huge integer and then use the recursive reduction mod div base 16 to create this. I have a much faster shortcut. And going backwards is just as easy. Or yeah, let's say you are given this hex number. Well, you just look up in the table, like what's a 9? It's a 1001. What's a 3? 0011, etc. And by the way, you know, sooner or later you will have to, you know, basically immediately learn like what this stands for, right? Because we use powers of 2 all the time, and we use binary all the time. So you should you can just as well start learning to training yourself to do that fast. Okay. And the spaces that I'm putting here, these are just for you know, my mental ease, right? Like there's nothing sacrosanct about them. They're just so that, you know, because the algorithm divides it into chunks of 4. Okay, now how many, this is the common question that you will encounter. You have some integer range. You want to represent it, let's say base 2 or base 16. How big bit strings or hex strings do you need to represent integers of such range? So here is, okay, so ask yourself a question, for example, like if you have digits base 8, an arbitrary base, and you want 5, you have 5 digits. What's the largest integer they can represent? It's 8 to the 5 minus 1, because the maximum integer you can represent with 5 base 8 digits is, well, you just take the maximum, right? Like this is like a 9999 base 10. It's a 77777 base 8, right? It's the maximum number you can represent. And that gives you this summation. And recall, this was a summation of a geometric sequence. So with a 7 in front of it, right? So it's 1 plus 8 plus 8 squared plus 8 cubed plus 8 to the 4th, etc. What is that? It's 8 to the next power minus 1 divided by 8 minus 1, which is 7. But there is a 7 in front of all of this. So that part cancels, and you get this. Okay. And indeed, this has to be, because if you did these arithmetics base 8, the way you would represent it is, well, what is an 8 to the 5 base 8? You would represent it this way: 5 leading zeros and a 1. That's this. So if you switch yourself to arithmetics base 8, then this thing minus 1 gives you that, right? Because if I want to subtract 1 from here, well, I have to borrow from here and get a full thing. But what's a full thing? In a decimal, that's a 10. In base 8, it's an 8. So 8 minus 1 gives you 7. And how can you cannot borrow anything, right? Because it's a 0. So to borrow from the left, what are you going to borrow? An 8. And minus 1, okay? So that's why you're going to get all of these, right? So, or conversely, add a 1 to this, and you'll see that you will get that base 8. Okay, so that's an easier thing. If you have, and that works in general, right? So in general, there was nothing special about either the length or the base. If you have given base and a certain length of an integer, the highest integer you can represent is this one, b to the k minus 1. Okay. So now, okay. So if I know how long my representation is, like how many bits I have. Let's say I have 16-bit strings, and I'm interested in how big of integers they can compute. Okay, it's 2 to the 16 minus 1. All right. But let's say I want to go back the other direction. I have certain integers I want to represent. I know my integers are up to 30 million. How many bits do I need to represent them? Or how many hex digits I need to represent them? So because going from the length of a base, of a number base b, to the highest integer is an exponentiation, going back, it's a taking logarithm. Okay, so if n is at most b to the k minus 1, so therefore n plus 1 is at most b to the k, so therefore k is at least logarithm b of n plus 1. So therefore the nk was the length digit, the number of digits, right? The length of the representation in that base, right? So for bit strings, like it's intuitive that you would call it the length of the bit string, right? But you can apply the same concept to any representation. So because the length has to be at least this logarithm, and length has to be an integer, right? Like you cannot have half a bit. So you have to take a ceiling. Okay, and so that's how you would compute. Okay, I have 32 million. I want to the highest number I want to represent. I take 32 plus 1, and I take a logarithm, whether it was base b, base 2, or base 16, if I want binary or hex, and I know how many digits. Reminder to everyone: if you skipped sections on logarithms and exponentiation, and section on floor and ceilings, go back, right? Because we do use this, right? We didn't test it at the time when you were supposed to read that stuff, and I said that, okay, we'll use it later in the class. I'm not testing it now, so but read it eventually. So that's the reminder. It's there for you to refresh. My problem is that I forgot my watch. So, and if I have a presentation, I do not know how big it is. Okay, and now I killed the presentation. I think screen sharing stopped. Okay, good. So I have like about 10 or 12 minutes. All right, that was not the smoothest. Okay, yes, super not smooth, because now I will go and I have to restart the presentation. Okay, so a few minutes remaining. Let's look at exponentiation algorithms. Okay. We will use exponentiation in crypto systems, and they're also used in other applications. But I want to do modular exponentiation. Okay, so I have a base and an exponent and a modulus, and I want to compute what's the base to the exponent, but modulus n, modulo n. So I'm not interested in what this result is as a full integer. I'm only interested in what it is mod n. So here is this sort of trivial algorithm, right? Like if an exponent is a 0, then I'm assuming exponents are that all of these are integers, and positive ones too. So if x is 0, then I just return 1, right? Because b to the 0 is a 1. And if it's non-zero, then I compute whatever, the smaller one power less, and I multiply it by the base, right? So what's 2 to the 5? Well, it's 2 to the 4 times 2. What's 2 to the 10? Well, it's 2 to the 9 times 2. And it's a modular multiplication, right? So remember the table multiplication tables modulo and all the operations modulo. That's what's hitting here. Okay, so this is correct. It's like an immediate proof. The problem is that if let's say my key is an exponent, and this modulus is some huge modulus, it's like some prime, large prime. Maybe it has 1,000 digits. So the exponent also has 1,000 digits. So how much times is recursive? Well, if it has 1,000 digits, then well, yeah. So okay, basically, okay, forget about 1,000 digits. I mean, let's just take a number that has how many digits? 7. Okay, this exponent has 7 digits, not very many, and it's already a million, right? And this algorithm will take 1 million steps, 1 million modular multiplications. This is not very good, and it doesn't bode well what happens when you're trying to run it on a number that has 9 digits, so it's a billion, or 12 digits, so it's a trillion, etc. Right? This is just going to scale horribly. The short way to say it is that the length of this number, call it k, or call it t, the length, the running time of this algorithm is exponential in that length. It's 2 to the length. Okay, length in binary. Okay. Oh, one thing I didn't mention this. One thing that comes up from the fact that this one, that so I have some integer, and this tells me how many bits I need if I represent this integer base b. Okay, so let's say I will represent it in decimal, so it's base 10. In bits, it's base 2. In hex, it's base 16. What's the relation between these different logarithms? If I compute this logarithm base 1 base, can I also fast estimate what they would be in other bases? Yes, because of the chain rule for logarithm computation. Well, I will write it next time we meet, and there are such exercises. So the bits here, these lengths will be related by the relations between logarithm of 10 base 2, 16 base 2. These are constants. They don't depend, so they're just constants in front of this equation, what the base you take. So in some asymptotic terms, it doesn't matter what base you take. Therefore, when we talk about an algorithm that's exponential in the length, we don't even have to say what base, because regardless of what base to take, relation between a description of a number base 2 and a description of a number base 10 is it's a constant factor difference between them. Okay, so it is an exponential time algorithm, and it is not, fortunately, the only one. So here is the recursive algorithm that is much faster, and I believe we have seen this already, just not in the guise of a modular arithmetic. So again, the same base case. If the exponent is a 0, I return a 1. But otherwise, I divide my exponent by mod 2. So I do a x div 2. and then compute the exponentiation of the base b to this half smaller exponent. Okay, and then depending on whether the division by 2 was exact, that's the case where x mod 2 is 0. Well, if that was a full, if x div 2 was simply half x, then if p is b to the half x, then p squared is b to the x, right? And if the division was not exact, so x mod 2 was a 1, then I have to multiply one more power of b. I have to multiply this p squared by b. Okay. So in binary, I don't have to compute these x mod 2. If my x is encoded in binary, then x mod 2 is just the last digit of x in binary. And x div 2 in binary is all the bits of x except of the last one. So I take I chop off the last bit and I shift them to the right. That's what division by 2 is in binary. So this is not an expensive computation. This is just the last bit of x, and this is not an expensive computation. I'm just shifting the bits of x. So there is really no computation there at all. The computation is in these squares, modular squares. So I can rewrite this algorithm faster like this. I do the recursive call, which computes b to the x divided by 2 integer division. Okay, so a floor. And I take whatever this gives you and it gives me, and I square it, and then I multiply by b to x mod 2, which is either a 0, in which case this b vanishes, or it's a 1, in which case there is a b here. This algorithm is therefore called square and multiply, because that's what you do here, right? All you're doing here is you're squaring and possibly also multiplying by the base. You're multiplying if the bit. So what are you do? If you recurse this, what happens? You're going from the last bit to the previous, to the previous, to the previous, to the previous. And what are you doing at every computational step? Well, you are going to actually kind of remember that you have to square and multiply. So when you reach the bottom, you get a 1, and then you square it, which is nothing, and then multiply by power of b. The leading bit has to be 1, or otherwise it wouldn't be a leading bit. So at the beginning, you're going to have a power of 1, which is 1 times b. And then you take that and you square, you return it to the next one, right? So what's the next guy gonna do? Square that and multiply if the next bit from the left side was a 1, and leave it alone if it wasn't. So at every shift from bit to bit to bit, all you're doing is you're squaring and multiplying by b if there was a 1, if the bit was 1, and not multiplying by if the bit was 0. So hence the name. Yeah, I have the proof of correctness of this algorithm, and also kind of like a different representation of the algorithm. So which might or might not, depends, on you, really be a more convenient way for you to think about it. But I think there's no point like trying to rush the proof in the last minute. So I will end here.